Alright, today we're tackling the second half of Chapter 18, Sampling Distributions. Last time we did proportions, today we're doing means. This is the address, the web URL for the applet we're going to use. Let me go ahead and get to it and kind of give you a picture of what we're looking at here. What you're going to want to start with is you want to draw 3 graphs across the top of your paper. We're going to look at 3 different types of distributions. Uniform distribution, distribution that's skewed to the right, and a distribution that's roughly normal. We're going to look at what happens to the distribution of sample means. If you keep taking samples that are small, like size 2, what is the distribution of means going to look like? Versus if you keep taking big samples of size 30-ish, what is the distribution of means going to look like then? Go ahead and start with this. Draw those 3 graphs at the top, and you're going to want to draw 2 rows of empty graphs that will fill in. And these are going to be the graph for x bar. So this is the sampling distribution applet at the web address that I showed earlier. I think I'm also going to link to it on my website. We'll start with uniform distribution. So uniform distribution means every number from 0 to 32 is equally likely to be picked. So it's kind of like you're putting a bunch of numbers in a hat. Every number has an equal chance of being picked. I'm going to start with samples of size 2. Here's the idea. This is one sample of size 2, 2 numbers. And they're both kind of on the high end, like 31 and 28-ish. This blue dot is the mean of those 2 numbers. I'm going to take another sample, 2 numbers, and it's going to plop down the mean of those 2 numbers. The mean should be right in between those 2 numbers. That should make sense mathematically. 2 more numbers, another mean, and basically we're going to keep taking samples of 2 numbers and dropping down the means, and we're going to look at a distribution of the means of samples of size 2. Now I'm on my 8th sample now, and as you can see we're getting a bunch of means over and over and over again. And a uniform distribution means every number across the spectrum is equally likely to be picked. It's not weighted normally or skewed or anything. Every number has an equal chance of being picked, which would be great for just a plain vanilla random number generator. Now this could go on for a while. I've gone through 17 samples. I'm going to hit this 5 button, which is going to simulate 5 sample means, and it's going to plop down 5 and then 5 more and then 5 more, and basically we're going to keep picking samples of size 2 and keep plopping down the averages. Now if I hit the 10,000 button, it's going to go through 10,000 samples of 2 numbers and plop down the averages of those 10,000 samples of 2 numbers. And this is what the distribution of means ends up looking like. I'm on 30,000 samples, 40,000. Let me go ahead and hit the 100,000 button, which adds 100,000 samples. Now a sampling distribution is basically a large number or an infinite number of samples. If you keep taking whatever statistic you're looking at, in this case the mean, our distribution of sample means ends up looking triangular. And for size 2 it actually is triangular if you're picking from a uniform distribution. So we're going to go back to this slide from earlier. For samples of size 2, the distribution of means is going to be triangular. Go ahead and draw a triangle wave. That's not something you need to know per se, but it's good to have in your notes. X bar means, again, you're taking a graph of the averages, the means of samples of size 2. Back in the applet, I'm going to go ahead and clear this. We're going to stick with the uniform distribution, but this time I'm going to make the sample size really large. So now we're going to pick a sample of 25 numbers. And you can see all 25 numbers plopping down, and every number from 0 to 32 has an equal chance of being picked. And finally, this blue dot represents the mean of those 25 numbers that were picked. I'm going to do that again, another 25 numbers. And after 25 numbers are selected, it's going to average those 25 numbers and plop down the mean of that sample, which is that blue dot. So now we've got 2 sample means from samples of size 25. I'll do one more just to kind of give you an idea. You're taking a sample of 25 numbers, and we're going to graph the mean of those 25 numbers. Now I'm going to go ahead and hit 10,000 and go through 10,000 of these samples. And here's the idea. When you get to a larger sample size, the distribution of sample means starts to become roughly normal. And as I get to, let's just say 500,000 samples, and then we'll call it that, you can kind of see the distribution. This is what the distribution of sample means is going to look like. For whatever reason, the means get compressed towards the middle. You're not likely to get a mean that's really far out from the middle because you're taking so many numbers. And the average is likely to be somewhere close to the middle when you're taking that many numbers. So if we go back to the sheet of graphs here, for a sample of 30-ish, we did 25, but that's close enough. The distribution of means is going to be roughly normal. And again, that's the distribution of sample means. If you keep taking the averages of samples of some large size, it's going to be roughly normal. Now we're going to go over to skewed distribution. Go ahead and clear this, and now I'm going to change this to a population that is skewed. I'm going to change this to make it even more skewed. Skewed to the right, which is saying the numbers on the left are going to be a lot more likely to be picked. That's the height of the probability distribution. The height of the distribution gets smaller and smaller to the right, which means the numbers above like 14, 15, these numbers have a much lower shot of being picked. I'm going to start with small samples, samples of size 2. 2 numbers, plop down the average. You got one number on the high end, but most of the numbers are going to end up coming from the low end. Again, 2 numbers, plops down the mean. 2 numbers, plops down the mean. These are kind of on the unlikely end of the scale, but that happens every now and then. So again, here's the big idea. You're taking a sample of numbers, you're averaging them and graphing the means of these samples. And we're really interested in that graph that's in blue, the distribution of sample means for a really large number of samples. Now, a lot of the means are coming down from the left side because most of the numbers are going to come from the left side. Every now and then you'll get a number on the higher end of the scale, which gives you a mean that's kind of maybe close to the middle, but you're not really likely to get an average that's on the high end because that means you'd have to get both numbers on the high end, and that's really unlikely. You might get one number, but probably not 2 numbers on the high end. As you can see, a lot of the means are coming down on the left-hand side. Now, if I fast forward and do 10,000 samples, here's what the graph of means is going to look like. Skewed to the right because most of the means come down on the left-hand side because that's where most of the numbers are going to come from. Every now and then you'll get a mean that's higher up, but probably not way high up in the 30s. If I had 100,000, you can kind of see how the shape forms out. The distribution of means for a small sample is going to be skewed to the right still. That's for small samples of size 2. Now let's go back and clear this, and let's do, instead of samples of 2 numbers, let's do, again, the biggest that we can get with this simulation, samples of size 25. Here's one sample of 25 numbers. Most of the numbers are going to come from the left-hand side, as would be reflected in the population distribution, and that blue dot is, again, the mean of these 25 numbers. Let me animate a couple more. That's a sample of 25 numbers. Most of them, again, coming from the low end because that's where the probability distribution is the highest. And again, that blue dot represents the average of those 25 numbers that we just picked. I'll do one more before I hit the fast forward button. Again, most of the numbers coming down are on the left-hand side, and occasionally you'll get one in the middle, or very rarely one on the very high end. So let me go ahead and fast forward, and again, these are sample means, the means of samples of size 25. If I do 100,000 samples and plot the mean all 100,000 times, this is what the distribution of means starts to look like. Roughly normal, because we're getting a big sample. As you get a bigger sample, the mean is a lot less likely to be high up because that means you have to get all 25 numbers on the high end, which is very unlikely with this probability distribution. So once we start taking large samples, the distribution of means starts to become roughly normal. Now finally we'll move on to the last population we're going to look at, a normally distributed population, which means the numbers in the middle are most likely to happen. As you get further away from the middle, numbers are less and less likely to be selected. We'll start again with samples of size 2. Pick two numbers, plop down the mean. Two numbers, plop down the mean. And we'll keep doing that a handful of times to get a few sample means. Now again, the sampling distribution is the theoretical distribution of an infinite number of samples. So I might get like 500,000, but in theory, for the distribution of means, you're looking at if you took like millions and millions and millions and millions of samples, what would the shape of the distribution look like? Now for samples of size 2, I'm going to go ahead and fast forward and do like 5, and then 5 more, and 5 more. And if I do 10,000 of these, and another 10,000, and another 10,000, and then 100,000 on top of that, the distribution of means for samples of size 2 starts to look roughly normal, with a decent amount of spread. So for small samples of size 2, the distribution of means is going to be roughly normal. It's going to be a little smaller than the population distribution, and we'll talk about how to calculate spread in just a bit. Big samples of, I don't know, 25-ish, 30-ish. 25 is the biggest we can go here. Here's a sample of 25 numbers drawn from a normal distribution. Most of the numbers are going to come from the middle, hence the normal distribution. Here's another sample of 25 numbers. And once we pick all 25 numbers, the blue dot is going to be the mean of those 25 numbers. And because you're going to get so many numbers in the middle, chances are the mean is going to be in the middle. That's what happens when you get a bigger sample size. The mean is going to be closer to wherever the numbers are most likely to be drawn from. I'll do one more. Now, if you think about it, in order to get a blue dot way on the edges, that would mean all 25 numbers would have to come from way around the edges, which is really unlikely, which is why so many of these means are coming down towards the middle. Because if you take the average of a bunch of numbers, that's where the mean's probably going to come down. I'm going to go ahead and fast forward and just hit 100,000. And if you get 100,000 samples, you can't really see the definition of the shape, but it is going to be roughly normal, but the spread is going to be a lot smaller because most of the means are just going to come from the middle. You don't have as great a chance for a mean to be further away from the middle with the bigger sample size. So for largish samples of 30-ish, it's going to be roughly normal for the distribution of sample means, but it's going to have less spread than for samples of size 2. Now here's the big idea from this. We are allowed to use the normal model if the sample size is big enough, then the distribution of means is going to be roughly normal, no matter what the shape of the population. Even if it's uniform or skewed, as long as you're taking means of big samples, again, at least 30-ish, then the distribution of means is going to be roughly normal. Or, if the population is roughly normal, then the distribution of means is going to be roughly normal no matter what the sample size is, even if the sample size is small, like 2. The name of this phenomenon is something huge in statistics, and this is called the central limit theorem. As long as the sample size is large enough, the distribution of means is going to be roughly normal. Now, large enough is a bit subjective, and it kind of depends on the scenario, but for the purposes of this class, we'll say 25 or 30-ish. If the sample size is at least that big, you can use the normal model no matter what.